Hello viewers, welcome to the second video on iron carbide phase diagram. This is a continuation to the previous video. So if you have not watched my previous video, please do watch it. And for those who have already watched it, thank you for your likes and subscription. Also, please give your comments below. This is prepared mainly to focus on frequently asked questions and about the triple T diagram. So these are the some of the content that we have already discussed in the previous video about the iron carbide phase diagram and how it is categorized into steel and cast iron based on the percentage of carbon, and followed by some steel transformations that we have seen, and here particularly in the eutectoid reaction, followed by its microstructure. So the main focus for this video is on few frequently asked questions about iron and carbide phase diagram. First one, is iron carbide phase diagram a true equilibrium diagram? And why cementite has only 6.69% of carbon to form a compound? The carbon solubility in FCC gamma iron is more than BCC alpha iron, though the packing factor of BCC is less than FCC. Why? And what is the important amount of ferrite and cementite present at different carbon percentages? And what makes steel such an important engineering metal? Then we will be looking into some of the other important continuation to iron carbide diagram, that is about triple T diagram, which is nothing but time temperature transformation diagram, or it is also called as IT diagrams and all. Then we have CCT, continuous cooling transformation diagrams. So let's start by knowing what is lever rule. This is very important for us to calculate some of the uh, points in the iron carbide phase diagram. Especially we will be able to calculate the amount of phases present, also along with its composition in a two-phase region. So the lever rule mainly has two statements. The first statement is about when you have a two-phase composition to be found out. The first rule says that draw a horizontal line at a given temperature. This line is also called as a tie line, and this intersects at 2 points, in one here and other one here. So they mark the liquidious line at this point, and another one marks a solidious line at this point. At this point, I would like to remind you the line joining all locus of all the points which mark the beginning of solidification is what we call this as a liquidious line, and the locus of all the points which mark the end of solidification is what we call this as the solidious line, which is marked by this line. So when you draw a horizontal line which cuts this liquidious line and the solidus lines at 2 points, at one at here and one here, they directly, when on dropping to the base line, will give you the corresponding compositions directly. So when you drop onto the baseline for the solidus line, you'll get the solid composition, and when you drop onto the baseline for the liquidious point, you will get the liquid composition. So in this case, you can see directly the liquid composition is 80% of B, and the remaining will be 20% of A. Similarly, for solid composition, you have 10% of B and 90% of A. So this is the first rule. Second rule is draw a vertical line at the given unknown composition, which where we need to find out at that particular two-phase region. So when you draw a vertical line, it will cut the tie line into two halves. So like in this case, and it is in the two-phase region. Now you can make this into a line diagram where you can divide this into M, N and O, where already the composition has been given directly. The solid composition is 20B and liquid composition is 80B. and unknown where we need to find out is at this 60. So the second rule states that when you draw a vertical line, it will divide the tie line into two halves, and the faces amount of faces present is inversely proportional to the distance between the two, or the divided line is inversely proportional to the amount of faces present in each of its face. So when I say inversely proportional, if at all I want the solidus composition or percentage weight percentages, I need to take the other side length. Like in this case, I need to take this length divided by the total length into 100. So this itself I can show you, like the difference between 60 and 10 is 50, and 80 and 60 is 20. So the percentage of liquid present is MO minus NO, which will leave me this length, which itself is shown here in this case. MN is distance is 50 by the total length is MO as usual into 100. This is for liquidius. Why liquidius? Because liquidius opposite side you are supposed to take. Solidus opposite side you are supposed to take this one, NO by MO into 100. So they are inversely proportional. The same thing in with respect to this particular example, the liquid composition, you got it as yeah, 50 by 70 into 100 is 71.43 percentage of liquid weight percentages are present. Similarly, the solid, you may also do it by 1 minus or 100 minus you can consider, and then you may write it as 28.57, or you may also calculate it this way. So this is very important for us to calculate the different weight percentages, even for iron carbide phase diagram. We are going to see that. So the first question is iron carbide diagram a true equilibrium diagram? So what do you think? It is the reason why we have just said phase diagram, not the equilibrium phase diagram. So the answer is no. The reason behind is, since carbide, iron carbide is metastable, it transforms into graphite after a prolonged durations of time. As you can see in this dashed lines, it shows the transformation of graphite. Instead of forming cementite, graphite. So even in the liquid, directly at eutectic reaction, instead of forming a austenite and cementite, here you can see this dashed lines represents this iron graphite system at higher temperatures, and this is mainly the greater stability and closest to the full equilibrium iron graphite system. So in general we say this as a not true equilibrium diagram, and also iron carbide diagram, iron carbide itself is a metastable one. Then why the cementite Fe3C has only 6.67 percentage of carbon to form a compound? So cementite has got a composition of one atom of carbon and every three atoms of iron. Now the atomic mass of carbon is 12 grams per mole and the iron is 56 grams per mole. So the percentage of carbon is goes like this, 12 by 12 plus 3 times of 56, which is multiplied by 100 will give you 6.67 percentage. So that's the reason why at 6.67 percentage of carbon, it forms a compound, and it is interstitial type of compound. Then coming to the next one, this is very important. Now here we have the carbon solubility. It's quite interesting to see that for this iron carbide phase diagram, you have allotropy. So you have three forms of phase transformations at different temperatures. One is delta iron, then you have gamma iron and alpha iron, where delta iron is BCC, gamma iron is FCC, and again alpha iron is BCC. So you know that these crystal structures have different types of its packing factors, and in spite of the packing factor of BCC is less than the FCC, you have the maximum carbon solubility in FCC, that is austenite or gamma iron, is maximum 2%, and whereas the BCC delta iron is 0.18, and you also have seen alpha iron ferrite is 0.025 percentage of carbon alone. So why what is the reason behind it? So atomic packing factor of ferrite is 0.68 percentage, that is it has more available free space relative to the austenite FCC, where it is 0.74 to host the interstitial atoms. Basically in BCC, interstitial positions are at the midpoints between the cube center and the face center, and in FCC they are at the midpoints of the cube edges, and that is a one of the reason why you have this kind of difference in the solubility, because of its position. The structure itself has got some difference where interstitial positions are available, where the carbon atoms are supposed to go and position themselves. And another reason is the largest interstitial sphere that would just fit in the BCC has the radius of 0.36 Armstrongs, whereas the largest interstitial sphere that would just fit in FCC has a radius of 0.52 Armstrongs. Since FCC interstitial positions are larger, and therefore the distortion in the regular crystal structures are much lower. Hence, the solubility of carbon in austenite is 2% greater than the solubility of carbon in ferrite, which is 0.025 percentage. It is like you are trying to fit a carbon which has got 0.66 Armstrongs of atomic radius to fit in BCC and FCC structure, where the maximum radius in BCC is just 0.36. So the regular crystal structure will distort much larger in BCC. If you see the same thing in case of FCC, it has got the largest sphere that could fit is 0.52. Even though the distortion is there here as well in case of FCC, the distortion in case of BCC is much less. Sorry, in case of FCC is much less comparatively. I'll also show you with the diagram. So here you can see this is BCC crystal structure and the possible carbon atoms which can go and fit and form a either octahedral interstitious positions or tetrahedral interstitial positions. The same thing in case of FCC, you can see the octahedral and tetrahedral interstitial positions, but their positions are different. And when you are given a distorted crystal structure, obviously it will have an effect on the overall solubility. Then coming to the next one, what is the amount of ferrite and cementite present at different carbon percentages? And now for this, we are supposed to calculate using the liver rule which we have just discussed. So here at I'll consider it in four or three different cases. First case, let me consider in the less than eutectoid composition, which is a hypo-eutectoid region. I'll consider at 0.4 percentage of carbon. So at this 0.4 percentage of carbon, and let me consider at 723 degrees centigrade itself, where it will form the proeutectoid ferrite and perlite. So for this, like I said, you are supposed to take the horizontal line, which I call it as a tie line, and then the vertical line, which will divide the tie line into two halves, and the amount of faces present are inversely proportional to its lengths. So I can convert this into a tie line, and here we don't have liquidious and solidus like we have discussed for the general example. Here we are supposed to see what is the mixture that we are going to get in the final product. So here after this reaction or below this line, you are entering into a hypoeutectoid region where we get a proeutectoid ferrite as well as a perlite. So I am supposed to consider between these lengths which we get the ferrite maximum solubility, perlite maximum solubility. So that will be nothing but ferrite will form at 0.025 percentage of carbon and perlite at 0.8 percentage of carbon. And you are considering for 0.4 percentage of carbon what are the amount of phases present, or what is the amount of ferrite composition and what is the amount of cementite. So like usually what we do, we have supposed to calculate this distance and then this distance, which zero point 0.4 minus 0.025, which is nothing but 0.375, whereas 0.8 minus 0.4 will give you 0.4 as well. So at 0.4 percentage of carbon, the percentage of prototype ferrite is nothing but, if I want ferrite, I am supposed to take this length, which is NO by the total length, MO into 100. So that will be 0.4 by 0.4 plus 0.375 will give you 0.775 into 100, which is nothing but 51.61 percentage. Similarly, for perlite, you may also take it as 100 minus 51, which is also right, or you may also calculate for perlite, I am supposed to take Mn by Mo into 100, which will give me 0.375 by 0.775 into 100 will give me 48.39 percentage, more or less 50-50 percentage at 0.4 percentage of carbon. Now the next one will be at 0.8 percentage, where I am supposed to calculate not for the perlite, it is the mixture that we call it as a perlite. So when it is at 0.8, we get 100% perlite, which is a mixture of ferrite and cementite. So this is where you need to be very conscious about, because this diagram represents only up to 2% of carbon because it is about the steel, but in this steel you are getting a mixture of ferrite and cementite, which is not shown in this table, in this diagram. That cementite will be formed at 6.69% of carbon. The previous slide itself we have discussed. So you are supposed to draw this lever rule between ferrite and cementite, and that's where ferrite will be formed at 0.025% of carbon, which is known to you already, and perlite at 0.8% of carbon, and the cementite which has to go till 6.67% of carbon, like shown in this case. So again, the difference between 0.8 minus 0.025 is nothing but 0.775% of carbon. And here for the cementite, we get 6.67% of carbon minus 0.8, 5.87% of carbon. So this is very similar. So the percentage of ferrite is OQ. So ferrite, this side you are supposed to consider, that is OQ by MQ into 100, which is 5.87 by 6.645, because it is addition of both total length divided by total length. So 6.645 into 100 is nothing but 88.34% of carbon, sorry, ferrite. Then if I want a cementite, I am supposed to take this length, which is nothing but MO by MQ into 100, which will give me 0.775 by 6.64 percentage into 100, which is nothing but 11.66 percentage. Then coming to the next, let me consider at 1% of carbon. So at 1% of carbon, also it is in hypereutectoid system, wherein the mixture will be proteictoid, cementite and perlite. So I'm supposed to take the distance only till the perlite, that will be 1 minus 0.8, which will be 0.2, and till the cementite, because I'm going to get the proteictoid cementite here, so which will be 6.67% minus 1, which is 5.67. So for 1% of carbon, percentage of perlite will be PQ, perlite, so opposite side, PQ by OQ, total length, into 100, which is 5.67 by 5.87 into 100, which is 96.59% of perlite. And for proteictoid cementite, OP by OQ total length into 100, which is zero point 0.2 by 5.87 percentage into 100, which is 3.41 percentage of cementite. So this is how at any given percentage of carbon you may find out the different percentage of ferrite and cementite present, or for that fact you may consider it for any composition for any kind of phase diagram. And it is better if you can use a graph sheet, you will get the divisions also possibly very close to the true equilibrium diagram. Now the next important question which we all must answer is what makes steel such an important engineering metal. So I'll give this one of the reason based on the previous calculations that we have already done it. So we have considered 0.4 percentage of carbon, 1 percentage of carbon, and I am going even for 2 percentage of carbon in the similar way. You may also try it out and calculate. I got it as perlite as 79.56 and projected cement as 20.44 percentage of carbon. So if I draw this diagram, which just to generalize or to round it off and then put it in how much percentage of projectile ferrite and perlite are formed at each of its steel zone, it is very interesting to see that at zero point 0.4 it is close to 50 percentage of projectile ferrite and 50 percentage of perlite, right? So this is where you'll get. And at zero point 0.8 obviously 100% of perlite, right? Then at 1 percentage of carbon, perlite is 96.59 and the remaining 3.41 itself is prototype cementite, like you can see here. And the remaining at 2 percentage of carbon you have a prototype cementite 20.44 percentage of, and then you have the perlite 79.56 percentage, right? So this shows that we have quite different variations that is possible with respect to ferrite, perlite and cementite. And we also must remember what is the property, mechanical property of ferrite, perlite and cementite. So here ferrite is very soft and ductile and perlite is medium hard. Cementite on the other hand is very hard and brittle. So suppose if you select somewhere at 0.4 percentage of carbon, you are selecting a material which is having ferrite 50% and 50% of perlite, which is giving you a combination of some soft ductile to medium hard. And this is possible when you vary the percentage of carbon accordingly and choose the microstructure accordingly. And for pure perlite you may get medium hardness, and when you select something close to the cementite, as the cementite percentage increases, you are increasing its hardness and brittleness. So this is how you may use the percentage of carbon to select for different applications of engineering materials. So this is where steel has this unique possibility of varying these compositions and getting different type of properties, mechanical properties in a given metal. So that makes the steel very important engineering metal. Now coming to the discussion about the triple T diagram, which is time temperature transformation diagram. Before that, we are supposed to understand why this is so important. So this comes under the phase transformations in steel. So here we know that austenite is not stable below 723 degrees centigrade, and this austenite transforms into other forms of perlite and cementite or even ferrite. So while transforming, how this transformation is taking place is being studied at different time temperatures, and this is being plotted on a single curve. And the way we do that is also having two different ways. Like if you know take to that subcritical temperature and then cool it rapidly, then you may get in this in this way, like perlite, which is coarse grained. Then we may get perlite with fine grain, then upper bayanite, or then lower bayanite. And this is possible when you decrease the transformation temperatures. So when you keep on decreasing these transformation temperatures, you may get different types of microstructures, starting with coarse grained perlite, then fine grained perlite, then you may get upper bayanite and then lower bayanite. The other way of doing that is by I'll call this a decrease in temperature or transformation temperatures, which we call it as a isothermal transformations, or also called as IT. And this is what is time temperature transformation is all about. Then the other way of doing that is when you cool at increasing cooling rates. Now when you have very slow cooling, then we have it with the first formation as perlite coarse grain, then perlite fine grain, followed by perlite and martensite, and then martensite. This is by increase of cooling rate. So this is how you are increasing the cooling rate. I'll show you how it is possible, and this is what we call it as a continuous cooling transformation, in short CCT. So basically, to understand the difference between this triple and CCT is, triple when you take the austenite and cool to some subcritical temperature and then rapidly cool it. So here we are just trying to see using the diagram how we are getting different phase changes in of steel, and that is what is triple diagram. And when you can increase the cooling rate by using different medium to cool to the room temperature, so the medium will have different cooling rates of bringing down the crystal structure or bringing down the microstructure. So the basic difference is in the way we do that, so decreasing the transformation temperature and increasing the cooling rate. Obviously this is not practically possible, whereas this one is practically possible, that is CCT is practical, because here we are trying to increase the cooling rate, which is by using different medium. Okay, so coming to the time temperature transformation diagram, how are we supposed to draw it? So it plots between time in seconds, and you can see it is plotted even for 0.1 seconds, still 10 power 5 seconds, which is, we consider it as 1 day. And obviously for temperature, and we are supposed to take austenite transformation. So this time temperature transformation diagram is for austenite uh, microstructure, how it is transforming to austenite in steel. So austenite in steel is stable only about 723 degrees centigrade, and below that it is not stable. So this first transforms the into different forms, and here also we have the beginning of transformation and the ending of transformation. So we have also taken 150% of transformation. This is how it will look like. So this marks the beginning of transformation, 50% transformation, 100% or end of transformation. And you can see it looks like an S curve, or it has this is where the nose is, right? So we call that as nose region, which is around 550 degrees centigrade. And this is the zone where the austenite is unstable. And like I said, this is the start, this is finish line, and 50% finish. So this marks perlite start and perlite finish. Then you have bayanite start, bayanite finish, as well as martensite start and martensite finish by this temporary horizontal lines, which is marked by dashed lines. So we get perlite coarse one, perlite medium, and then you have perlite fine grain. Then you have upper bayanite, bayanite, and lower bayanite, and followed by martensite start finish, and this is where you get the total martensite. Now, like I was mentioning in the previous slide, if you uh, try to see the hardness for these transformations, you will get coarse perlite, which is around 20 Rockwell hardness. Then you have increasing its hardness values, and finally the most hard microstructure will be martensite. So if at all I take this austenite and draw till this point where I'll be able to transform to perlite. So this is basically when you cool it very slow, which is what the equilibrium diagram also talks about. Then you have, when it cuts at this particular zone, you may get as a perlite, then BNite, and followed by, when you cool very rapidly, martensite. And this martensite, why is it so hard, is because you are not giving much time, or in fact to that matter any time at all, for carbon to come out and form any other intermediate products. So whatever the amount of carbon present in the austenite will be cooled rapidly by not giving any diffusion to take place. So it is also called as a diffusionless process, and it is a super saturated solution of carbon mixed in austenite. So that makes the martensite very hard, and also it has got very fine, evenly distributed uh, cementite in the ferrite mixture. Then, like I said, continuous cooling transformation, wherein you are supposed to draw the cooling curve with different in its way we cool it. So it is done by taking the austenite as usual. So let me consider this austenite and the furnace, and it is heated around 8 or 723 above percentage of temperature. And then from there, if I cool to a particular cooling rate, which I call it as a very slow cooling, and it is possible to do that by cooling in the furnace itself. So when you cool it very slowly by keeping the components in the furnace itself very slowly, it may take some days, or 1.5 day to cool to room temperature, and that is considered to be as very slow cooling. And then you may also use another situation where I need to cool it moderately. So in this another situation, let me take the component out and keep it in the outside, which is like air cooling. Then cooling at a moderate rate, where you need to form a moderate cooling transformation. So I may use oil cooling, where I take out from the furnace and dip it in oil medium, and that will cool it in a medium cooling rate. Then you also have one cooling rate where exactly it touches the nose portion tangentially. So this is something which is important. Again, we'll come back to that. Then cooling very rapidly. Now by cooling very rapidly, I mean cooling in water. So taking the component from the furnace and then quickly cooling or quenching it in a water medium, that is rapid cooling. So you can see this is what, when we superimpose the triple diagram with the rate of cooling, continuous cooling, and then you may get the austenite transforming, starting with here, and then finally we reach here. So above the nose region we have perlite. So this is where perlite is formed, and this is done by cooling it in furnace itself. Then we have something which is above the nose region as well, which we have perlite transformation, and also you have, if you cool it little bit close to, then we may also cut it at uh, where we may get perlite and martensite. Then we also have a cooling rate which is oil cooling, where we get martensite, and along with martensite we may also get a mixture of perlite and bayanite. And like I said, this one cuts tangentially. So this is where you have the critical cooling rate, which is nothing but the minimum rate of cooling at which the austenite is transformed to martensite. So this is neither the rate of cooling is too high nor too low. We are designing it such a way that it exactly touches the nose region or tangential to the nose region, and which will transform the austenite to martensite 100%. And this is the rate of cooling which is required for getting austenite to martensite transformation. So this is called as critical rate of cooling. So I hope I was able to explain some of the few important frequently asked questions, and then some phase transformations of steel about triple T and CCT curve. I have already created one small questionnaire for this kind of subject, and you may participate and give your feedback inputs. Thank you for your time, and do subscribe and let me know what you feel like and mention them in the below comments. Thank you.